Andreas and Luca presenting today. So they're both PhD students at the University of Toronto, interested in ML and quantum chemistry. And so today they're going to present their paper about predicting Hessians directly with MLIPs. So the floor is yours. And also for people who want to ask questions, there should be like an FAQ section. So just ask the question there and we'll just read it to the presenters.
Yeah, that would be great. So feel free to ask questions during as well. And I guess Ali, he will interrupt me. Perfect. Yeah, hi from my side as well. So we call this project Hessian interatomic potentials, or just HIP for short. And it's really about extending MLIPs that you know and love, like maze or esin or equiformer, to also predict the Hessian in addition to the energy and the force. So machine learning interatomic potentials, the whole idea is we can do expensive calculations with density functional theory, or DFT. And we really want to bring down the cost by just training a machine learning model to predict usually the energy and the force of DFT. And we do this with graph neural networks, these machine learning interatomic potentials. And these are just machine learning models that take in the coordinates, like the XYZ positions of the nuclei and the atom types. Then we do a few rounds of message passing, and at the end, we predict the energy and the force. Then we usually have some data from DFT on the energy and forces and train against that. And the force here, yeah, it's just the gradient of the energy, as you might know. So it's the gradient with respect to the input positions, the nuclei positions. And we can either predict the force directly, or we can do autograd from the energy to get the force. So in this work, we were now interested in the second derivative of the energy, and that's the Hessian matrix. So if we have like 3 atoms, and we have some interactions between them, then the Hessian will be like a matrix of 9 by 9. So here, we have like 3 colored blocks times 3 colored blocks, and these are the 3 atoms. And then each block itself is 3 by 3 for the 3 spatial coordinates XYZ. So in general, this Hessian matrix of second derivatives will be 3n squared, if that makes sense. So it gets quite large. So why do we care about the second derivative? So we really came from transition states. So if you want to model a chemical reaction, you don't just need the minima, you also need the point of highest energy in that reaction, and that's a saddle point, the transition state. And if you remember from high school, like saddle points, you need the second derivative to identify them. And in higher dimensions, that's the Hessian eigenvalues. So this is, if you go to Orca and call like frequency analysis, that's what it does. It looks at the Hessian eigenvalues. And if you want to find a transition state, you usually use the eigenvector of the Hessian. So the Hessian really comes in handy if you want to model chemical reactions. You can also use the Hessian to do faster geometry optimization, so relaxations. So instead of doing BFGS or just following the force, you can use the Hessian at every step to get a faster convergence. This is very similar to like second order optimizers in neural network training as well. The last one is a bit more involved theory-wise, and it's like nuclear quantum effects. So you often use them if you want to model activation barriers or like entropic corrections. And what it basically is in Born-Oppenheimer, we act like the nuclei are not moving at every MD step, like simulation step. But we can make a correction by having like a Taylor expansion. And in the second order, we get a harmonic oscillator. And then the Hessian eigenvalues are related to the frequencies of that. So basically, if you have the Hessian eigenvalues, we can do these extra corrections that we often use. And now Luca's going to take over and talk a little bit more how we can get these Hessians.
Yeah. Am I sharing right now?
No, can you try again?
Okay. Thank you.
And to answer one of the questions in the Q&A, We will post the recording in the YouTube channel.
Wait, I'm sharing the wrong screen. Okay, that's fine. Yeah, great. Okay,
Yeah, we see.
so yeah, so we just heard Hessians. Obviously, they are very useful. Now the question is, how do you calculate them? Obviously, you can use DFT for it with something called coupled perturb-Kohn-Sham. However, it's really expensive. So if you think about your favorite range-separated hybrid Kohn-Sham DFT has a formal scaling of N4, then the DFT, the Hessian calculation bumps it up by one complexity going to N5. And what that means in practice, it's if your DFT calculation would take something on the order of like 10 seconds, then your Hessian can take on the order of a few minutes. So clearly, this is really expensive. But then we could say, okay, but we have MLIPs now. Can we get the Hessian from them? And well, you definitely can. So the same way how you can get forces with autograd, you can do a second times autograd to get the Hessian. You could also take a direct force head and take autograd. However, this is really expensive in both cases. So if you take double autograd, then what you have to do is that you have for every row of your Hessian, you have to take in a Hessian vector product. So that means in total you need 3n, where n is the number of atoms, 3n Hessian vector products. And each Hessian vector product is about the cost of 4 times of a single forward pass. So you are looking at the cost of roughly 12 times number of atoms compared to the normal forward pass. And then the same if you would do it with a direct force head and you do autograd, then you're looking at 3n Jacobian vector product. They're a little bit cheaper, but it's still really expensive. It's about double the cost of a normal forward. So you're looking at about 6 times number of atoms on cost of a single forward pass. And you can also see this practically. So here we were plotting the cost of calculating in Hessian with an MLIP for a different number of atoms on the x-axis. This was an Equivariant V2 model. And you see, okay, normal forward pass, roughly 30 milliseconds, peak memory slightly grows. Okay, everything nice and dandy. But then if you do AD Hessians with a direct force head, so direct force, 3n Jacobian vector products, you see this already quite a lot more expensive. If you do it with double backprop, so take the energy, take 2 times the backprop, then you see this grows really steeply. And just for completeness, if you don't use AD, but you use finite differences from your forces, then you look at even steeper cost in terms of time. At least your memory is low in that case, though. So clearly, this is really expensive. There's also another thing that if you do not train your Hessians with DFT Hessian data, they're actually not that great. So, you know, similar to how you have to train your forces with DFT forces, even though you could technically just train the energy and then take the derivative, those aren't very good, right? And there's something similar with Hessian. So if you just train on energies and forces and you just take the derivative, they are not very good. On top of that, if you do train your Hessians with DFT Hessian, they are very expensive. The training is very expensive. So what we said, given all of these drawbacks, it's very expensive to do MLIP Hessians. You need to train them anyway. Why don't we train a direct Hessian readout head? And you can redo that with any equivariant graph neural network that has UofT carrying features. The only thing is that for energies, you need L0s, for forces, you need L1s, and then for Hessians, you need MLIPs features up to L2. So for people that are familiar with MLIPs, you will know what I'm talking about. If you don't, then just think about there are different types of features in a MLIP, and you need a certain type of features to build these Hessians. And the reason why is that in physics, a lot of properties transform in a specific way if you transform your molecule or the coordinate system of the molecule. So we have invariant features where if you transform the molecule, then the value just stays the same. So that's an energy, for example. Forces are equivariant, which means if you transform the molecule with some rotation matrix R, just think about multiplying every force vector with the same rotation matrix. So they transform along with the molecule rotation. Now the question is, how do Hessians transform? And it turns out they transform like a Cartesian tensor. So what that means is each of these 3x3 subblocks here transform with a rotation matrix Q like this. So you multiply from the left and from the right with the rotation matrix. And now the question is, how do you enforce this? Or how can you build a network that predicts the Hessian where each of these subblocks transform this way? And to do this, we use this this formula. It's if you come from physics, it's basically just going from coupled to an uncoupled. Going from an uncoupled from coupled to an uncoupled angular momentum basis. So you would have some features up to L2. These are H here for every IJ atom combination. So IJ indexes the atoms, L indexes here from L0 to L2, and M just indexes within the arrow. And then here we have the Clebsch-Gordon coefficients, where you basically go, you contract over this L and M here, which you have on the right, and then you restrict your L1 and L2 to 1, which means that the M1 and the M2 goes from -1, 0, 1, right? And this -1, 0, 1 is essentially indexing your 3x3 subblock. So this way you can go from this feature vector here into this small subblock matrix. So now that we discussed how we can transform these features into the matrices, we have to think about what kind of features do we need. So we can think about a MLIP doing some message passing. You will end up with some latent features for every node, so for every atom. And then you could do the trick we just discussed, and you would end up with the diagonal. Obviously, that's not enough. We also need the off-diagonal blocks. And the way you can do that is by just using the messages, the message passing that we already have in our MLIPs. So what we would do is we would take an MLIP, we do a sequence of L message passing layers, we have some latent embedding, and this now goes into the Hessian readout head. And this Hessian readout head does another set of message passing, but instead of aggregating the messages onto the nodes, we just keep the messages. And we just consider them as features for our Hessian, for our off-diagonal blocks. And then the node features for the diagonal. And so we can do this, we can do the reshaping trick we just discussed, and then we can assemble this full Hessian. Now, there's another nice feature. Oh, and then in the end, the Hessian is also symmetric, so you can just symmetrize it by just adding the transpose.
I have a question.
Yeah.
Yeah. So when you said that you take the messages as being like the interaction term of the Hessian, how does it work when you have like two nodes that are very far apart and they don't have the message?
Very good question. I'm just coming to that in a second.
Okay, thank you.
Yeah, so there's actually a feature, not a bug. And this is because we know from quantum chemistry that Hessians are sparse. So you can actually show it mathematically that they have to be sparse, where you basically have a decay of the Hessian terms. And as we said, message passing already is defined on a cutoff. And now you can use a different cutoff compared to the one for your normal MLIP message passing. If you want to be safe, you take a little bit of a larger one. But in general, we know that the interactions of the Hessian terms further away, they need to decay to 0. And now this is very nice because we can just reuse this whole machinery of message passing and cutoff radii to make use of this sparsity to bring down the scaling further from an ON squared to an OFN scaling. So basically our entire Hessian prediction will scale linearly in the end, assuming that your MLIP under the hood already scales linearly. Yeah, so that's for the theory. I guess I can just ask if there are any other questions regarding the theory. If not, then Andreas will take over talking about experiments. Okay, no questions, then I give it to Andreas.
Yeah, thank you very much, Luca. So, yep, in our paper, we have experiments for small molecules. In particular, there was a data set released last May on 1.7 million DFT Hessians. So these geometries come from the transition 1x dataset, if you know it. So it's basically small molecules up to like 25 atoms that only HC and O. So quite a nice testbed for our MLIP. And we're going to be using Equiformer v2 as like the basis, where we just add these hip Hessian predicting head. We could also have used Maze or Esin or Yuma or any other model you like that has equivariant features. And in particular, if you look at experiments in our paper, what we did is we even froze the whole network that already existed and just trained this extra prediction head that we added to just have like a super fair comparison, like the energy and forces are completely the same, and we just look at the Hessian. Although I'm also going to show you that if you train energy, force, and Hessian end to end, that's even better than fine-tuning just the Hessian prediction head. So let's go back to this picture. This is basically our baseline, right? So the whole point is we want to speed the process of getting Hessians up. And here we had before, if you take finite difference or AD Hessians, and down here in green is a forward pass. And if we now combine this to our direct prediction, we basically end up at the same speed of just a regular forward pass of an MLIP. So when we zoom in, we can see that compared to a forward pass, we have like a 25% overhead to predict the Hessian. And this makes sense. We're basically just doing one extra round of message passing, right? So that's about like 1 layer. And this happened to be like a 4-layer Equiformer. So that works out to roughly 25% extra. And then the memory is almost the same. You have a bit more memory if your cutoff radius is bigger than during the message passing step, but for the small molecules, it's like almost not noticeable. So with this, we were already like super happy, right? We basically sped up getting the Hessians by like 100x for small molecules. But of course, like also the accuracy matters. So we took these baselines from the previous paper, and they trained on the same data set. So what they did is they actually used the 80 Hessians during training to make the 80 Hessians better. So I'm not even showing the untrained 80 Hessians that you get by just downloading some checkpoint. They did like trained on the same data, including the Hessians. And now if you compare this to our direct prediction, we basically lower the Hessian mean average error to like about a third, which made us very happy. In particular,
sorry, here when you say Equiformer v2, it's like you take autograd of Equiformer v2 without training on Hessians.
So this is actually already trained on Hessians. So
okay.
If you just take Equiformer v2 and train on energy and forces, the error is like way worse. And they trained already on the same data set.
Okay, thank you.
And yeah, but yeah, training on these 80 Hessians is quite expensive, as we talked before. So they use like 8 GPUs and about like 2 weeks, I think, to train each of these 80 Hessian models. Whereas for us, it took like 2 or 3 days on a single GPU to converge. Yeah, of course, also the downstream effects matter. So in our paper, we have some detailed experiments for transition state search, geometry optimization, and this nuclear quantum effect that I talked about. I think we have a bit more time, so maybe I'll just go into the first few results to kind of give you an idea. The first one, like speaking of accuracy, is like 0-point energy corrections. So these are nuclear quantum effects that you often want to compute as corrections when computing activation barriers. So you're usually not interested in just the activation energy, but the now I'm blanking. The Gibbs free energy difference, and there you compute use the extra corrections of the Hessian eigenvalues. So this is really similarly just like the sum of the Hessian eigenvalues of the weighted, mass-weighted Hessian. So it's basically a metric of how accurate are your Hessian eigenvalues, right? And if you look at like 80 equiformity 2, and then going down to directly replicated ones, we can see that the eigenvalues especially get a lot better. Like the difference is even of the eigenspectrum is way bigger than if you just look at the mean average error. We also improved, like tested on transition state search. And basically in transition state search, you often have like a first step to get a rough estimate, which is something like nudged elastic band or a growing string method. And then you have a local search, which is like often it's partitioned rational function optimization, which is something like if you use Celler, for example, it's doing the same thing. And there you use the Hessian eigenvalue or try to approximate it with BFGS. And similarly here, the eigenvector, like the eigenspectrum of the Hessian, is a lot more accurate if you predict it directly. And so we got some gains on transition state search as well. We also did faster geometry optimization with Hessians. So it's basically just relaxations. And here we look at the steps until convergence. And I just want to highlight here these green ones. So these are like first order methods. So they only use energy and forces. And these red ones are using AD Hessians or finite difference ones. And you can see they frequently diverge. So they're like two blobs up here where it just did not converge in the number of steps we gave it. And then compared to using our directly predicted Hessians every step, we get like a big speed up. And these blue ones here, they use some form of BFGS, so an approximation of the Hessian, which turns out is also pretty good in for small molecules. Right. Then I want to end with just one result that made me very happy. I think it's our newest version on the archive. And that is what happens when we look at the energy and force error in terms of the number of training samples. So this is a log-log plot where here on the x-axis we have the dataset size basically. And we can see that the energy and the force error goes down if you have more training samples. Now what we did is, so this is just like regular equiformity 2 with energy and forces. And now if you also include the Hessian, our error actually reduces. So even though now that we also have to predict the Hessian, our training is like 25% slower, having the extra information from the Hessian actually improves our data efficiency at the same like training time. So I thought it was really cool. Yeah, I think we teased a little bit in the beginning for those who were here, but I think there's a lot of future possibilities that we can do here. The first one is go to more interest in chemistry, right? So especially if you're interested in catalysis or enzymes, like transition state search there, it's just much more interesting than doing these small molecules that we did. And that we could also extend it to different models like Maze or Yuma or Eason. And then I also think we can just use Hessians much more than we used to. Like in so many codes, if you look, there are like workarounds, like natural elastic band, for example, where you try to only use the force and avoid the Hessian in every way, just because it's so expensive. But if we actually have the Hessians super cheaply, then I think there's much more we can do on the algorithm side as well. So with this, I just want to say thank you very much. And if you have some CPU hours lying around and you want to calculate some DFT Hessians for some interesting chemistry, then hit me up. I would be very happy to help.
Thank you so much. That was a great talk, Andreas and Luca. So I have a few questions in the chat. I'll start with the first one. So there's a question saying you reference the paper by Lee et al. Where they learned the Fock matrix, but they argue that MAE is not enough and that it's problematic to just use MAE. Do you think that this is the case with Hessians as well?
Yeah, so you're talking about the loss function or just the metric MAE? I mean, I can answer both. So I think I agree. We usually, so I first had a bar plot of just like computing the L1 error, the mean average error of the Hessian, and I agree it's usually not that interesting. So we're usually interested in the eigenspectrum, right? So for transition state search, it's like the eigenvalues, the eigenvectors, and for classification or zero-bound energy, it's the eigenvalues of the Hessian that matter more. And for the loss function, we experimented around a little bit. And we do have a loss that also like targets the eigenspectrum. That's similar to some losses that were used in like Hamiltonian prediction before. And in practice, it does improve the training a little bit, but it's also like a bit slower. And so just for simplicity, like we have it implemented and we have the results in the appendix, but we default to just regular mean average error because that difference is not that big and it's just simpler, I think.
But so I guess that this is different from the forces, like the energy conserving case, where you want the forces to be linked to the energy, or it's less important in the applications. Is there like any application where this is important and you would want it?
Yes, I mean, Luca, do you want to answer this? This is really your ballpark.
Yeah, no, you're right that in general, we need to always look at the task at hand and see whether or not conservative like integrability is important. One of the main points you make also in the paper is that if you look at the mainstream use cases for Hessians in quantum chemistry, integrability is just not important. We also have in the paper some more mathematical arguments for when it is fine to have something that violates integrability and when it's not fine. And yeah, it just turns out that the way people use Hessians, it's just not important. You can also see that already from just looking at what people do, what the alternative is, and that's BFGS. And BFGS itself is also not in any sort energy conserving. So that there you always see that it's not important. There are some like super arcane niche use cases where I think it is important. In nuclear quantum dynamics, you can technically use Hessians and you might get something similar to energy drift with forces. But as in large, like for all the mainstream stuff, it's much more similar to something like a geometry optimization in direct forces, where direct forces are fine for energy minimization. Because everything you use Hessian is always something like similar to energy minimization, or it is some sort of single point calculations, and there you just don't have these issues of a curl error accumulating over some integration time.
Great, thanks. And maybe related to what you said, so like you said that it's used with BFGS, like to accelerate, and I guess you showed some results on how much faster is it. Is it also like compensating with the fact that the model is a bit slower? So you like end up relaxing your structures way faster at the end?
Yeah, I think for the cases we were looking at, BFGS is already good. Although we are faster, it's just that there wasn't that much breathing room because the structures are small, so they all converge pretty fast. But it is even in real time faster. Yes.
Yes, exactly. So BFGS is really good for these like small molecules where you already converge in like 5 steps with BFGS. So if you're bringing that from 4 to 5, there's not much gain there. But I think it would be interesting to test it on like larger molecules. I think in general, like if you have any kind of optimization where you have a trajectory, then you can always approximate your curvature in the direction you're going, right? With something like BFGS. But for like single point calculations, like the nuclear quantum effects, or if you want to check is this a transition state or not, then there really is no approximation that you can do. And so for the single point calculations, having the Hessian directly is like super interesting.
Thank you. And last question from Mathilde. Just curious, could you extract materials ZPRs from ZPEs? And I don't know what those stand for. So I don't know if you know.
Yeah, so you said ZPE, was that it? Or did you ask?
Could you extract materials ZPRs from ZPE?
What are material ZPRs?
Mathilde, you can unmute yourself.
Yeah, I'm not a chemist, so it could be totally the case, and I just don't know what it is.
Can you hear me? Okay, yeah.
Yeah, we can.
I just know that in like condensed matter, we relate the ZPEs to like 0-point renormalization, which is essentially like how the energies are corrected for these effects.
Mm-hmm.
And they're kind of challenging to calculate. So I was wondering if, you know, just by curiosity, if you had sort of looked into it. It's fine if you haven't. It's fine. Okay.
Luca, do you know?
No, I think just generally you could do this whole machinery that we did right now with a couple of adjustments for periodic boundary conditions. You could do it for materials as well. So as long as ZPRs, again, I don't know what they are, but as long as you can get them from the Hessian, it should be doable.
Okay, pretty cool. Thanks. Nice talk.
Yeah, no, thank you for the question. I think also something that we should be working about is like, I guess we're always like working in this Born-Oppenheimer image, right? So everything that includes movement of nuclei, we can only do like perturbatively. So if you can do it with DFT, you can do it with our model. If you can't do it with DFT or like couple cluster or whatever, then
yeah, that's what I would figure. But I wondered if you had looked into it.
Yeah, thanks for the question, though.
Okay, thanks, Mathilde. Maybe I have one more question. So, like, currently the way you frame the problem is very grounded to the fact that you're using equivariant models.
Mm-hmm.
Do you think this could work as well if you use the non-equivariant model, or are there limitations in doing that?
Yeah, no, this is totally right. And that's also something I'm curious about. Like, maybe, so first of all, our method is just designed for like how to do it with serial harmonics, right? If you just have a non-equivariant model, then you could just construct any kind of readout to construct a matrix and just try out what works best. So we don't touch that at all. But I think what's also might be also interesting is like maybe non-equivariant models are smoother, and you can just train them on the energy and get good forces, or just train on the forces and get good Hessians. I think this is an open question. But in general, one of the perks of these equivariant models is the data efficiency. And we talk about calculating DFT Hessians, since they are so expensive, I think having equivariance is nice.
So it's likely that we would need data augmentation as well on the non-equivariant part, even for the Hessian.
Yeah, well, so if you do data augmentation and don't use an equivariant model, then I think you don't need to worry about how you construct your Hessian, right? You can just, I mean, you can use the same idea of message passing, but you just don't need this Clebsch-Gordon step.
All right, thanks a lot. That was great. Any other question, Luis?
I have one. I'm just curious if you had any tricks on how to train with the Hessian now, because like I know that when you train with energy and forces, you weigh them differently at the beginning and throughout the training. Is there anything special about training with the Hessian as well?
No, that was actually the like pleasantly surprising thing. Like once we got it to run fast, it just works. There were, I mean, I played around a little bit with the Hessian weight. I don't even remember. I think it was weighted similar to the force, roughly, but there was nothing special. Maybe the only things we talked about before, we used the L1 loss instead of the L2 loss. So mean squared error just tended to be a bit less stable than just L1 loss. Like you had bigger gradient spikes. But other than that, everything we tried worked.
Cool, thanks.
Okay, I think we can wrap up. Thank you for the very nice talk. And I guess people who have additional questions can reach out to you by email, right?
Oh, yes, please. And yeah, if you feel free to use the repo, and if something doesn't work, please write me. And if you want to use a different model and you want to adapt it, then also feel free to reach out, I think. And I'm very happy to help anytime.
Awesome. Thank you so much for the presentation.
Yeah, thank you for the invitation.
See you guys.
Okay, guys.
Thank
Have a
you.
good day.
Bye-bye.